Okay, students, so in this experiment we will be working on quantum analog. So what is a quantum analog? So we are using acoustic waves or sound waves to simulate quantum mechanical experiments. Okay. In this particular experiment we will be using sound waves to simulate a one-dimensional solid. Okay. You have to read the manual to understand the exact analogy between the sound waves and electron waves in a one-dimensional lattice. Okay. So we are making this is basically a representative of your one-dimensional lattice. How we are making this? So as you notice, there are these blocks, tube-like things. So these are like cylinder-like objects like this, of different shapes and different sizes are there. So this is one particular size, let's say. So we have put 12 of them, and in between two of these cylinder tubes, we have something called an iris. So this is like an iris. So this sort of represents your atom basically. Okay. So what you see here, you see a one-dimensional lattice of atom placed periodically, right, after equidistant gaps, because all the cylinders are of the same length. So all the these irises are equidistant. Okay. So in this particular experiment, I think we have 5 centimeter cylinders. Okay, so that means what? That is, this is now like a lattice, one-dimensional lattice. These are the atoms, and there is one-dimensional lattice, and we are putting in sound wave. Right? So sound wave, as you know, when you put it inside a tube, what will do? It will set up standing waves. Right? But now this is like a tube where the periodicity is broken because of the presence of this iris. Right? So if we did not have any iris, and if we had like this 12, there are 12 of these tubes of 5 centimeter, then that would mean 60 centimeter length, right? Total. So that would mean now the standing waves, you can predict what kind of wavelength will be set up over there, right? Standing wave. So because if your length is L, then that L must be an integral multiple of lambda by 2. So you know what lambda will give you a standing wave or resonant wave. So whenever, for example, if I change the frequency of lambda and put sound waves in this tube, I will get a resonance condition at that point. Alright. And because whenever it hits that resonance condition, it will give one resonance, but then it can be an integral multiple of lambda by 2, right? The length is 60 centimeters. So that means there are multiple lambdas that will satisfy this. So you can set up an equation connecting lambda and length and n, where n is the integer. So for each n, you will get one lambda or resonant frequency. Yes. But here, what will happen is that we will still have those resonance conditions, but because the periodicity of the tube is broken, so now something else will happen. So this is like an electron wave that is moving in the crystal. So this is like a vector crystal, where the periodicity, there are periodic potentials because of these atoms, right? So now the wave functions will be different, right? Bloch wave function, as you know. So here also you will have resonant frequencies, but then there will be certain frequencies which will not be allowed. You will not see any signal from when you input that frequency. Okay. So these will represent your band gaps. Okay. Then there will be certain allowed, basically certain what will be your resonant frequencies. Those will be your allowed wavelengths or k vectors for the electron. Right? So as you know, if you have a crystal of length L, so what are the allowed k vectors? N into 2 pi by L. So that is depending on this L. Right? So there will be those allowed k vectors, but then there will be an entire region where there will be no allowed frequencies. Okay, so there will be no resonant frequencies you will find. So those will be your band gap. More details you will find in the band for this one. Now here I will just describe you the setup and the experiment. So you see these tubes are there and these irises are there. So this is this much we have discussed. So this is your one-dimensional solid. Alright. Now at the end of these two tubes there are two special tubes. Okay. So again, this one has a speaker, okay, and this one has a microphone. Okay. And the signal from the microphone is going into this controller unit, okay, which has multiple different electronic setups inside. Okay. So we discussed them. But this is the microphone. This is the speaker, which is getting again its input from here, again from the controller. But actually, the input from this controller is coming from where? It's coming from. If you look at it carefully, it's coming from this black wire. If you trace this black wire, you see this is going to your function generator. So this is your function generator. Okay. So you can generate any kind of sine waves. You can generate square waves. You can generate sawtooth waves. You can generate different kinds of waves. You can different amplitudes. You can put in different frequencies. Right? This is a typical function generator that you will see in electronics lab or physics lab. Alright. So now it's connected here. So it's giving some wave. It is sending some waves here. So that wave is fed. For example, it goes into this controller, and from here it's a speaker output. That means it goes to the speaker. So that signal is fed to the speaker. Again, the part of the signal you see is diverted, and using these are called splitters. Okay, so you see we got one, and then we connected it to this key-like object, connected it to the controller, and a part of it also went out and went to the channel 1 of your oscilloscope. Okay. So channel 1 is the Euro channel, so this is the input signal. This is the signal that is coming from the function generator. You see a clear sine wave over there. Right? Now, what are the other things here? What are the other connections meant for? So this is basically your input. This is basically the sine wave that you are putting into the tube. Okay, the wavelength that you are, or the frequency of the sound wave that you are putting into the tube, and you can control it using the function generator. Now, this is your microphone. So you input sound at this end, and you collect the signal from this end. Okay. So if there is a standing wave, this will detect an maximum. Okay. If there is no standing wave, it will not detect anything. Okay. So this is the detector that is placed here, the microphone. This feeds the signal now. You see, this one goes and feeds its signal to the microphone input. It is the input for the controller. Okay. So the microphone gives some signal that goes into the controller. So there is an amplifier here that takes this as its input, and then it amplifies the signal. There is an attenuator here as well to control the amplification factor basically. So you can, the more you increase the attenuator, the more it will decrease the signal. Okay. After the amplifier. And then what happens to the output? The output again we are taking and putting it into channel 2 of the cell, so that we can see the output. This is the output that is coming from your microphone. Alright. Now you see, as I told you, if I increase the attenuator, the signal, this thing will decrease. So you see, I am increasing the attenuator, the signal will decrease. I will increase the attenuator, decrease the attenuator, then the signal will increase. So this is basically for controlling the signal. Alright. Next, what we have, so this is all the connection. There is nothing else in there. So there is another part here which we will not be using. So there is no point in discussing it. Alright. Okay. So the remaining part I will discuss now. So, okay, as I said, we have feeding this frequency from here and coming to your tube here. Okay. So, as I said, we can increase or decrease the frequency. So at certain frequencies we will see resonance, at certain frequencies we won't see resonance, right? So how will we detect that resonance condition is there or not? How do we detect that? So let's say I am changing the frequency. I hope you guys are able to see. Let's say I am changing the frequency. I'm not sure if you will be able to see here. If you can see, this is now saying 220 Hz. Okay. So now I am increasing it. It's now 230 Hz. Now it's 240 Hz. So you see, as I keep on, now you see it's lesser. It's around 210 Hz. Okay. Now in each step I am increasing by 10. It's 220. Now you see the green signal. The green signal is the microphone output. It's coming from here, the microphone detector. So as I am increasing the frequency, the signal strength is increasing. You see, it's increasing. Keep on increasing. It's now gone outside the scale, right? What we can do, we can either change the attenuator or we can change the calibration of the scale from here as well. Right? This knob channel 2, this gives you what is the voltage per division. So if I increase the voltage per division, the graph will become smaller. Let me do that. So I am increasing the voltage per division. Now it's inside the scale. So I will keep on increasing. Let's say what happens. Keep on increasing the frequency. Now you see. Now it's decreasing. Now again, if I go back, now, so if I go back, now I will go back again so that I can clear this. So now I am increasing the frequency. I increase it one step, becomes around, I think, something around 280. Now increase it one more step. You see now it has increased. It's increasing. Increase it one more step. Now you see it is more or less same as before. Increase it one more step the frequency. Now you see it starts decreasing. So somewhere in between those 2 points, you had the resonance condition. Okay. So basically what you can do, let's say it's between 280 to 90. So there is a, this function generator allows you to sort of change the cursor. I don't think you will be able to see, but there is a cursor position there. So I can move the cursor around and change which unit I want to change. So because it was at the 10th position after the decimal point, so I was increasing the 10th position by 1 unit every time, okay, by one number every time. So 270, 280, 299. So I bring the cursor again, the first digit after decimal. So now I can change it 281, 282, 283, 284. So I can figure out, pinpoint out at what frequency I'm getting the resonance. Okay. So that will give me one resonant frequency. Okay. So in the experiment, you will actually have to do a sweep from close to 0, let's say 50 Hz, to 12 kilohertz. Okay. So that is a lot of range. So basically what you do is, we already have some reference data, so you can check that and sort of look at the frequencies while you are expecting the maximus of the resonances. And the actual experiment, as you read the manual, you will realize that it is conducted in a computer. So the computer can quickly sweep from 50 to 12 Hz, 12 kilohertz, 50 Hz to 12 kilohertz. You cannot do it manually, it will take you a lot of time. So we'll do step by step. So already look at the reference data and see where we expect the the resonances, and then we'll look at those frequencies. Okay, so if we do that sweep, what we will see? We'll see, if you go back and look at the manual, we will see that there are certain resonant frequencies, but after we hit a certain range, for a large range we will not see any resonance. Okay, the signals will almost be zero. If I keep on changing it, if I go up to let's say 1000 Hz close to that, I will see that the frequency signals, output signals, the green one is very close to zero. So that will continue. After some time again you will start seeing larger signals, and then you will see amplitude maxima, and then again it will sort of decrease a little bit. Then again keep on sweeping the frequency, it will again show you another amplitude maxima or the resonance. Again it will decrease, the amplitude will keep decreasing. Again it will increase like that. But then again it will hit another region where there is no resonance at all, for a large range of frequency. So these are the different band types. And within each band you are seeing resonances. If you go back again and look at your concentrated physics class, or even in your semiconductor physics class, you will see that the number of allowed K points for the electron is what? Is equal to the number of lattice points, right? So it should be around 11, 12, right? So if you do that, if you check within an allowed band, how many times you are hitting that resonance. For example, once we saw that, you can keep on increasing the frequency. So again you will see some other frequency is hitting resonance. Let me keep on, for example, increasing it. Let me press it back. So again you will see again it will become maximum at some point. Okay. See, it's again increasing. So this is another resonance. Okay. So if I keep increasing like this, will again, so we will encounter basically like 12, 11 different points. Okay. So that is equal to the number of lattice points. Alright, so this is basically the experiment. The full details you will find in the manual of what to do and how to calculate all those things. Okay. Other than that, we do not have anything else in this experiment. So what we will do in the next part of the experiment, for example, we have taken this. These are like 5 centimeter ones. So we can also take this one, this is larger one, 7.5 centimeter approximately. So that means we are increasing the lattice constant, right? Separation between two atoms, that is the lattice constant. So we are increasing the lattice constant. Also you can do is experiment with different types of lattices are there. So for example, you see, you look at this one has a bigger hole, this one has a smaller hole. So that would represent different types of atoms, right? So that will also have some impact on the band structure. So we can see the band structure. So ultimate objective is to sort of simulate electron waves using sound waves and see how the band structure depends on different quantities, different parameters. So we can change this one, we can change the total length as well of the tube. That would be just analogous to your total size of the crystal, right? So these kind of experiments we can do with this.